Alright, in this video we are continuing on with Unit 4C, which is all about using congruent triangles. And so once we have two triangles congruent, then we can use all of their corresponding parts are congruent, and we can prove a whole lot of things with that. Specifically today we're going to be talking about the perpendicular bisector theorem. And so as we're doing the perpendicular bisector theorem, I want to kind of pick apart what a perpendicular bisector is before we dig into what the theorem states. So think back to perpendicular. Perpendicular means that it intersects at right angles. So intersect at a right angle. And a bisector of a segment means that we are intersecting at the midpoint. Or that we're dividing that segment into two congruent parts. Alright, and so when we're looking at this, what this theorem is saying is in a plane, meaning in two dimensions. So I'm going to say 2D, meaning not in space. Just in a plane, a flat surface. If a point is on the perpendicular bisector, so in this picture, C is on the perpendicular bisector, then that point is equidistant from the endpoints of the segment. So what this is saying is, if C is on the perpendicular bisector, meaning CP is perpendicular to AB, and P is the midpoint, meaning P is dividing AB into two congruent parts, then this distance right here, CA, would have to equal this distance right here, CB. So equidistance means the distances are equal. So distances are equal. We want to actually prove this. And so in order to prove this theorem, below here we're given that CP is a perpendicular bisector of segment AB. We want to prove CA equals CB. So let's draw a picture of what this is, because we have some things marked here, but I want to draw a picture only based on what's given. So based on what's given, we have segment AB. We have CP as a perpendicular bisector of AB. So we'll put P here and C here. And so if I draw that line, it is the perpendicular bisector of AB. Here, what we're given is what the given is. They give us the second step already. CP is perpendicular and P is the midpoint, and this is using the definition of a perpendicular bisector. Let's go ahead and add that to our green proof sheet. So looking at our green proof sheet, this is in section 5.2, just the definition, which we've already worked through this definition in class, but now we're going to add it to the proof sheet. If we have a perpendicular bisector, and you can only have a perpendicular bisector of a segment, then we are perpendicular to the segment at its midpoint. And remember, for a valid definition, we need to be able to write this as a true biconditional statement, which means the converse of this conditional is also true. So if a line, segment, or ray is perpendicular to the segment at its midpoint, then it is the perpendicular bisector of that segment. So that's a definition that we need, and so we started with that right here in the proof. So now what we have to do is think through, well, how am I going to prove that this distance is equal to this distance? And once we draw on those distances, we see that we form some triangles. And so what I want you to do right now is pause the video and try and think through, how am I going to prove CA is equal to CB? Now that you've had some time to think through this on your own, I'm going to talk through my thought process. I see these triangles, and my thought is, well, if I can prove these two triangles congruent, then I would know their corresponding parts would also have to be congruent, and CA and CB are corresponding parts of the triangle. So my first goal is to prove the triangle's congruent. So when I'm looking at this, well, if it's perpendicular, I know that these are right angles, and a bisector means that P is the midpoint. So I'm going to say, well, then that's divided into two congruent segments. So the question is, how can I prove these triangles congruent? Well, I see right angles. Whenever I see right angles, sometimes I think RHL. Well, RHL, I would need the hypotenuse congruent and a pair of legs. I have a pair of legs congruent, but I don't have the hypotenuse is congruent. In fact, that's what I'm trying to prove. And I don't have So I can't use RHL. I can look at these right angles, not as right angles, but just as congruent angles, or congruent corresponding angles within the triangles, and this is a congruent sides, and if I have one other piece of information, I might be able to prove these triangles congruent. And what I see is that both of these triangles share side CP, so using the reflexive property, CP is congruent to itself, and now I can use side, angle, side. So we can prove triangle CAP congruent to triangle CBP using side, angle, side congruence theorem. And once we've proven that, then we can say, well, then their corresponding parts must be congruent. So CA must be congruent to CB. Well, if the segments are congruent, then they are equal in length, and that's how we get our final statement. So that's kind of the idea behind what we're doing. Go ahead and try and do this proof now on your own if you've not done so already, and then watch the video for my detailed steps on how to finish the proof. All right, so as we're doing the proof, we have to have next step. All we have right now is the perpendicular, so we need to say that there's right angles. So angle CPA and angle CPB are right angles. That's the definition of being perpendicular. So if perpendicular, then right angles. And we proved in a theorem earlier that if two angles are right angles, they must be congruent to one another because they're equal in measure. So angle CPA is congruent to angle CPB. And that's if right angles, then the angles are congruent. Now, I did not have to name these angles CPA and CPB. I could have put like a 1 and a 2 here and just name them angles 1 and 2, but I could not have named them angle P because there's multiple angles whose vertex is P, so just be careful of that. All right, so we have a pair of angles congruent. So I'm going to put a little A next to this so I remember, okay, we got our angles. We were wanting, what do we say, side, angle, side. And so we only have one pair of angles congruent so far. We need two pairs of corresponding sides congruent as well. And so when I look at this, if we use the fact that this is a perpendicular bisector, I know that segment AP is congruent to segment BP. Please make sure the order of your letters is correct, meaning the corresponding parts are written in the same order. So A and B correspond, P and P correspond. And that is because if midpoint, then the segment is divided into two congruent segments. So there's one of our pairs of corresponding sides. And now our final pair of corresponding sides is that CP is congruent to itself because of the reflexive property. And again, make sure your order of the letters is in the correct order. So C and C correspond and P correspond. This is the reflexive property of congruence. There is our third pair of corresponding sides. And now we have proved, using side, angle, side, that the triangles are congruent. So I can now say that triangle CAP is congruent to triangle CBP. And that's with the side, angle, side congruence theorem. The whole point of doing that was then to conclude that segment CA is congruent to segment CB, and that's because if triangles are congruent, or really any polygons are congruent, then corresponding parts are congruent as well. Now, the theorem says that the point is equidistant from the endpoints, which means that I need equal distances, not congruent segments. And so our final step is that if segments are congruent, then the segments are equal in length. And we have now proven the theorem. Because we have proven this theorem, let's go ahead and add this to our proof sheet. So take out your proof sheet. above here, oh, I said this was a theorem. This is not a theorem. This is a definition. Both of these were definitions. My apologies. This next one is a theorem. This is also in section 5.2, and it says if a point is on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. And that is a theorem. Now the converse of the theorem is also true. We are not going to prove the converse, but we will add this to our proof sheet. So if a point is equidistant from the endpoints of a segment, then the point is on the perpendicular bisector of that segment. And again, that is a theorem. So these are theorems that will come in handy. They really shorten proofs if you remember the theorems, but they're theorems that people often forget. They're kind of wordy. There's no shorter way to write this. So it's a good theorem to know, both the theorem and its converse. However, you can obviously go through all the steps that we did here in order to prove the exact same thing moving forward in other proofs. In addition to using this theorem in proofs, we can also use this to find missing values in a picture. So what I want you to do right now, example 1 says find x. So given the picture, I want you to determine using the perpendicular, or can you use the perpendicular bisector theorem? And if you can, find x. I say determine if you can because in order to use the perpendicular bisector theorem, you have to have a perpendicular bisector. So look through these problems right now, determine, do you have a perpendicular bisector, yes or no? And if you do, use that theorem to find the value of x, or the converse. Go ahead and pause the video, try these on your own, and then check your answers with the video after you've attempted these on your own. All right, so looking here, in order to use a perpendicular bisector theorem, I have to have a perpendicular bisector. Now these look perpendicular, but they are not marked perpendicular. And so here, we cannot use a perpendicular bisector. So we would say, not enough information. There's not enough information. You can't say that these two are equal. We just don't know that. Because you could redraw the same picture like this and say 3x minus 8 and have this guy as 2x. You still have your A, your B, and you draw this guy in. Call this line M, and now these definitely don't look the same, so you have no idea whether or not these two are equal or what their relationship is. For part B, I have perpendicular. These two segments are marked congruent, so I know x is the midpoint, or the WX bisects that segment, and so I know that WX is the perpendicular bisector of ZY, which means that these two segments are congruent. Or they are equal in length. So I know WZ must equal WY. In other words, 2x plus 11 must equal 4x minus 5. And now I can solve this equation for x. So if I do that, I get x is equal to 8. Looking over here, now I have that we are perpendicular, but I don't have that this is bisected. So I can't set these two equal, so I would say this is not enough info as well. So the only one I was actually able to do was B. The other two do not have enough information to solve the problem. All right, flipping to the back. I want to continue to use congruent triangles to prove other theorems, or to prove other statements. And so you are given that angle 1 and 2 are congruent, 3 and 4 are congruent, and you want to prove triangles BCE congruent to DCE. This now is using one pair of congruent triangles to prove another pair congruent. And so I'm going to highlight the two triangles I ultimately want to prove congruent in green. So BCE CE and DCE. And so when I look at those, what I have so far marked congruent would be these two angles. I know that they share this side, and so I can have an angle and a side, but I need something else. I either need to prove that these two angles are congruent, or I need to prove that these two sides are congruent. If these two angles are proven congruent, I would be using angle, side, angle. If these two sides are congruent, I'd be doing side, angle, side. I'm also given in this picture that 4 and 3 are congruent, so I can try and use that. So what I want you to do right now is think through, well, what can you do to maybe get enough information to prove these two triangles congruent? And my hint to you is that we're going to use one pair of triangles that we can prove congruent in order to prove the other pair of triangles congruent. So pause the video right now, attempt this on your own, and then watch the video to check your answer. Alright, so far I'm going to redraw these triangles. We know that we have an angle and a side, and we need some other piece of information. Now when I look at this picture, if I zoom out, I'm thinking, well, how many triangles do I see? So I see 1, 2, 3, 4, but I also see a top and a bottom, 5 and 6. I see this big one on the left, 7 and 8. So there's a ton of triangles. And the question is, which ones can I already prove congruent based on the information I have? And if I look carefully, what I see is this triangle here, I can prove congruent to this triangle here, the top and bottom triangle. So if I redraw those, it might be easier to see why I'm able to prove those congruent. I have these angles are congruent, these corresponding angles are congruent, and if you just look at the two blue triangles, we can see that these two segments are congruent. Well, if those two segments are, or this segment's congruent to itself and those angles are congruent, we can say these triangles are congruent by angle, side, angle congruence, which then allows me to say, well, every pair of corresponding parts are congruent as well. The question is, which ones would be helpful? And so the ones that are going to be helpful are the ones that are also in the green triangles. And those segments that they share are these guys right here. And so then I'm going to use the fact then that these two sides must be congruent, and now I can use side, angle, side here to prove the two green triangles congruent. Let's see what this looks like in a proof. We have our statements. We have our reasons. We always start with our given, so angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. That's our given. And we said, remember, the first goal is to prove these two blue triangles congruent. We already have the angles, the two angles. That's our AA. And now we need the congruent side. So we'll say that CA is congruent to itself. You could have said AC is congruent to AC. Just make sure that the letters are in the correct order. So C and C correspond and A correspond. That is our reflexive property of congruence. And now we have our angle, side, angle, and we can conclude that triangle DCA is congruent to triangle. Well, D in this picture corresponds with B, in that triangle. C and C correspond and A correspond. So double check your letters to make sure they're corresponding. You could have started with C here, but then you'd have to start with C here. So just make sure D and B correspond, C and C and A. And we were saying that those two triangles are congruent using angle, side, angle congruence theorem because the side is between the two angles. Well, the whole purpose of doing that was to prove that these two segments are congruent, or these sides of the triangle. And so we can say that CD is congruent to CB, and that's because if we have congruent triangles, then the corresponding parts are also congruent. And so now we have these two segments congruent. And now, for this one, we still have to prove that CE is congruent to itself. So we have the angles 1 and 2. We have the side. We need the other side. So we'll say CE is congruent to CE. and that is using the reflexive property again. Because we use the reflexive property to say two different things, you could have actually put this all under one statement up here earlier, which would be fine. I'm doing it in the order when I actually use it, so in that case I'm just saving it for later, but you could have put them all together in one. Now I have my side, I have my angle, and my other side, so I can say that triangle BCE is congruent to triangle DCE. And that is using the side angle side congruence theorem. And we have now used one pair of triangles to prove another pair of triangles congruent. So this is another way of using congruent triangles.